Welcome. So you too can fly to the moon, the Artemis mission. So going to the moon is really in the news lately due to the Artemis mission. This is the only video out there for taking you through the simple math and physics at a high school level of getting to the moon while simultaneously flying the mission using an actual simulator. The simulator is the Orbiter 2016 simulator, and it's something you can also download. Anybody can download it and run this mission. So all of this, the instruction as well as the controls, how to fly the spacecraft, is available via my book. It's called Physics for Space Travel, and it's on Amazon.com. It's endorsed by 3 former physicists and flight controllers, and you can also learn more about the book by typing Physics for Space Travel, quote unquote, at the YouTube search prompt.
NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later.
So fly to the moon, how do you go about doing that? Well, first you want to launch from the Earth's surface to a parking orbit about the Earth, and I'll do that shortly using an orbital simulator. You would launch from Cape Canaveral, the NASA facility in Florida. The next thing you want to do is circularize the parking orbit. This maximizes timing flexibility of the ejection thrust to the moon. And then finally, you want to enter into a transfer orbit and thrust to the moon. That's it. So what is an orbit? Maybe the greatest physicist who ever lived did a remarkable job at explaining what it is. Very intuitive explanation. And I elaborate on it in my book, Physics for Space Travel. It goes like this. Okay, Feynman's orbit. This is from my book on page 31. So the best explanation of an orbit that I've ever heard is from Richard Feynman, one of the great physicists. And so basically here is how he presents an orbit. So say you've got a satellite in space in a circular orbit about the Earth, and let's say this distance here is about 4.2 times 10 to the 7th. Okay, here it is right here. And the acceleration due to gravity at this distance above the Earth's center is 0.223. Okay, if you're on the surface of the Earth, it's 9.8, but the further you get from the center of the Earth, the less the gravitational acceleration. Okay, so in 1 second, this is going to fall this amount, 0.112 meters. Okay, this comes from Newton's second law. Okay, so if this is to remain on this circular orbit, okay, 0.112 this direction, it must fall this distance also in 1 second. Okay, so what is that distance? So Dr. Feynman came up with a really cool equation for computing that, and that equation is this right here: 2 times r, which is the distance of the satellite to the center of the Earth, times the distance that the satellite has fallen, square root. When you do that operation, you get 3078 meters. Okay, so therefore, at this distance above the center of the Earth, the velocity is 3078 meters per second. Okay, so for every 1 second that it falls is 0.112, it's going to travel 3078 meters in that same second and remain in this circular orbit. Isn't that cool? So the mission I'm going to fly here shortly using an actual simulator is leaving the NASA facility at Cape Canaveral, Florida, and going into orbit about the Earth. So the key steps. One, you need an upward force vector, a thrust vector, of the spacecraft that must exceed the weight of the spacecraft as well as the drag force. The drag force is the force on the spacecraft due to the friction of the air. Next, we'll fly due east. So why fly due east? The answer is the Earth rotates towards the east, so by flying due east, we don't have to overcome the linear velocity of the Earth of about 464 meters per second, which on a SpaceX rocket would be in excess of almost 3 times 10 to the 11 joules. It's a lot of energy, a lot of fuel. Once we get high enough, we'll kill the thrust. So what is high enough? Well, we want the closest approach of the craft relative to the Earth to be above the radius of the Earth, which is the surface of the Earth relative to the center, and that's 6.37 times 10 to the 6 meters. Once the thrust is turned off, because we're well above the atmosphere, there'll be no forces acting on the spacecraft, so it will remain in that circular orbit until some external force is enacted upon that, and there won't be any external forces acted upon it until we enter into a thrust to go to the moon. And that'll be in the next video. The other thing I'm going to do in this video, although it's not essential and NASA doesn't actually do this, but I want to illustrate this maneuver because it's an important maneuver, is I'm going to align the orbital plane of the spacecraft with that of the equator. And let me just show you a little bit more what that's about. Okay, so that's Earth. Okay, so this is the equator. And here is a launch from Cape Canaveral in Florida. Okay, Cape Canaveral is at about, I believe, 29 degrees, okay, latitude. Okay, so that's the angle, right, of the spacecraft flying due east relative to the equator. Okay, so therefore its orbit is going to be along this plane. Okay, it's going to orbit along this plane. Okay, so what I'm going to do is I'm going to realign the orbit to coincide with that of the equator. Okay, so when I am done providing the thrust at the ascending and descending nodes, the plane of our new orbit is going to be like this, where the angle of the plane of the new orbit relative to the equator will be 0. Okay, so let's fly the mission. Okay, so I'm going to take off from Cape Canaveral. I'm going to use the Orbiter 2016 simulator. I'll select on the Delta glider, DGS ready for takeoff. Okay, so there is the spacecraft. Doesn't look like a spacecraft. It's very futuristic. I'll use aerodynamics or the air or the atmosphere until the atmosphere is too thin, at which point I'll use rotational thrusters to provide the pitch to ascend to an altitude well above the surface of the Earth. And once I've done that, I can shut off the engines, and due to the near zero friction at that point, and according to Newton's first law, the thing will just circle the Earth. So let's get going. I'm going to hit F1 to go inside the cockpit, F8 to select my favorite cockpit, which is this one. And I'm going to select here the surface multifunction display on that one, and the orbit MFD in this one. All this is explained in my book. All right, next thing I'm going to do is look at the spacecraft weight. Okay, so the weight of this thing is, including fuel, is 26,000 kilograms, so that's about 267,000 newtons. So we're going to have 320,000 newtons as full thrust. That's going to exceed the weight of the aircraft and the drag. Okay, so therefore we'll have a positive thrust vector in the upward direction, and we will ascend. Okay, so I'm going to hit Control plus for thrust. Next, I'm going to use the 2 key on the numlock pad, and that will provide nose pitch up. And once we get to a sufficient speed, it will leave the surface of the Earth. Okay, next thing we want to do is we want to roll to a heading of due east. So that's 90 degrees. All right, so here we go. We also have to keep pitch above the horizon, so we continue to ascend. So here's our compass. Once this goes to due east, we know we've got the correct heading, and at that point, we just continue to ascend until the spacecraft is in orbit. It's pretty straightforward stuff. Slow out a little bit. Okay, so we're ascending pretty rapidly here. 60 degrees. We can start to level out now. We're approaching east. Here's our heading. We're almost at east. Once we hit east, exactly east, I'm going to go ahead and level out here. Here we go. We're straighten out. And go back the other way just a bit. Okay, looks like we've got it. Okay, we've got pitch below 0, so we're losing altitude. So I'm going to hit the 2 button again, pitch up. Okay, you want to keep this around, 20 to 30 degrees works. 20 to 30 will get you there pretty quick. Okay, so due east because we want to take advantage of the velocity of the rotation of the Earth. And now it's pretty boring. We're going to sit here and watch this indicator right here. It's right now it's 20,000. And once it exceeds 6.5 million meters, we can turn off thrust and know this thing will be in orbit because it will be above the surface of the Earth on both sides of the orbit. Okay, so we're maintaining a heading of east. Actually, I'm going to correct that a little bit. Bank a little bit left here. Okay, it's not quite on east, so I'm going to... Okay, level out. So we're definitely right on due east now, okay? Okay, I think what I'm going to do now is I'm going to just go ahead and cut this off so you don't want to sit here and watch me for the next 20 minutes, ascend to 6.5 million meters. And then I will, once I've got the 6.5 million meters, I will turn this back on so you can see where I am in orbit. See you in a few minutes. Okay, so welcome back. This is where my orbit ended up. So I continued to ascend and I got to my PER of 6.435 million meters above the surface of the Earth. Actually, it's above the center of the Earth. The radius of the Earth is 6.375, so I'm well above the surface of the Earth. Okay, so it looks, however, like my orbit, the green circle here, or the green ellipse, is falling inside the circumference of the Earth. It looks like I'm going to crash into Earth at this point. But that's only because I've got an inclination angle relative to the equatorial plane. That's why this appears like it is. It's really just rotated and coming out of the page. But I think what I'm going to do is I'm going to correct for that. I'm going to reduce this inclination of the orbit, and I'm going to have it relative to the equatorial plane. Okay, so this is the inclination of the orbit relative to the equatorial plane. That's a plane cutting through the equator, so 29.14 degrees. Okay, so we took off at Cape Canaveral, and when we took off at Cape Canaveral heading due east, it's got a latitude of about 29 degrees. So that's why we ended up with an inclination of about 29 degrees. So again, I'm going to take this to 0, and I'm going to do that by applying thrust at the ascending and descending nodes. These are the points of intersection between our orbital plane here, this green orbit, and the equatorial plane. Okay, the equatorial plane is the plane that cuts through the equator, as I mentioned before. Okay, so this is explained in great detail in the book, how to align the planes of two different orbits and why those thrusts need to occur at the ascending and descending nodes. So I'm not going to go into all that right now. I'm just going to do it, okay? So this right here is the descending node. I'm going to time travel a little bit to that point. Okay, so at the descending node, you want to provide a thrust in the normal or 90 degrees positive direction. And that's just going to nicely rotate this orbital plane. Okay, go a little bit further. Actually, that's enough. Now I'm going to provide a thrust, full thrust, in the normal direction, and the inclination should come down. Okay, we want this to go pretty close to 0. Okay, so the inclination has been reduced to 0.42. So that's pretty close to 0. Okay, so the planes are aligned. The orbital plane of the Delta Glider spaceship and the plane of the equator are aligned. The gray circle is now inside the orbital circle. And so the next thing we'll do, the next thing NASA does before leaving a parking orbit to the moon is to circularize the orbit, and I will do that in the next video. See you then.